Hello, everyone. It appears no one's shown up for the 1 o'clock class. I guess you're all going to wait for me to produce this video. So we're talking about chapter 4, and the last time we met, in class anyways, not in lecture this morning, but last time we met, we were starting into the discussion on Newton's laws of motion, which is chapter 4. And I told you how Galileo got in a little trouble with the court and specifically with the church and the Pope for his book and things of that sort. And part of his sentence was in-house arrest. Another part, of course, was that he was no longer allowed to study or publish about astronomy. So he decided that if he wanted to do anything useful, he's going to have to understand motion, because we knew at that time that there were 4 satellites at least of Jupiter. He called them the Medicean satellites, or Medicean moons. We now call them the Galilean moons: Io, Europa, Ganymede, and Callisto. And those 4 things did actually track with Jupiter. So the idea that, for instance, a bird sitting on a limb looking down on a worm, if the Earth was actually moving and the bird attempted to fly off of the limb, then the idea was that the Earth would leave the bird behind and wouldn't be able to catch the worm. So that was really one consideration of how motion worked at the time. And here was a case where we were looking at Jupiter, and everybody, including the Ptolemaic models, the Aristotelian models, even Tycho Brahe's model, all showed that that Jupiter was moving, and therefore the Galilean moons were moving and keeping up with it. So he went on to go and try to study that, and decided he had to study motion to make sense of it. So he realized that dropping an object was a little too complex for him to study. They didn't have good timepieces. They couldn't slow down time in any real way. So it wasn't obvious that when you drop this, was Aristotle right? This thing instantly took off at some speed proportional to its weight? Or did the object actually start off at 0 and speed up? Did it speed up in a random way? Did it speed up in a regular way? For instance, each tenth of a second, did it speed up by the same amount, or did the first tenth of a second it speed up by one amount, and the second tenth by a bigger amount, and by the third tenth a third amount? All those were open questions, and he realized he just couldn't study it directly that way. But he did realize, using what we would call similar triangles and trigonometry, that he could relate the vertical acceleration to, say, the hypotenuse type of acceleration on an inclined plane. And that's what he decided to study. And what he found is, when he rolled a ball towards an incline, it would go up an incline and slow down, slow down, slow down. When he rolled an object down an incline, it would speed up, speed up, speed up. And therefore, he argued that if he went exactly between an incline and a decline plane, i.e. a flat plane, he didn't expect the speed to change at all. That was basically the first iteration of what we call Galileo's law of inertia. An object in motion tends to stay in that state of motion because it has some quantity he called inertia, which is really just a placeholder to make you feel better about turning your back on what Aristotle had taught us. But that's what he came up with. He even went further. He realized, for instance, that if you rolled a ball down an incline and then immediately allowed it to ride up an incline, that the ball would almost get to the same height it started with. When he looked at that, though, he realized that it was bumping around, sliding, skidding, all sorts of stuff. So he realized, well, maybe if I polished it up and got it really a nice smooth surface, maybe it could go further. And sure enough, it did. It'd get even closer to the same height that it left from. So imagine it like on a half pipe, like people use for skateboarding and bikes and even motorcycles of this nowadays. But basically a ramp that goes down and then back up. So if you allow it to roll down one side, it almost comes to the other side at the same height. And he imagined that if he could actually perfectly sand it out, make it perfectly smooth, and get rid of all other forces, then he believed it would actually reach the max height. In fact, he went even further and imagined, what if I rolled a ball down an incline and then it hit a very, very gradual incline, so gradual that it'd have to go an infinite distance away to increase its height by, say, 1 millimeter or something like that. in that case, he realized probably the motion is one that's never going to change. So, despite what he saw, which was all objects when you roll them eventually come to a stop, he argued that if we could get rid of all these extraneous forces, an object would tend to stay in its state of motion. So he's really hypothesizing beyond what his technical skills and technical or technology would allow him. So that was a really big deal for the scientific revolution. One, that he was even considering experiments, but two, that he was actually going beyond what it could do. And imagine what it could do if technology wasn't a hurdle that he had to cross. And ultimately, he did come up with a law of inertia, which, like I said, he says it's as if an object has some quantity we call inertia, and that's an object's reluctance to change its motion, and that an object in motion tends to stay in motion unless acted upon by some external force. That ultimately became Newton's first law of motion, which says an object in motion tends to stay in that state of motion unless acted upon by a net external force. Okay, so let me give you a nice demonstration of exactly what Newton's first law tells us. So I'm going to share my screen, and I have a video from young Sheldon that I think is pretty fitting. Oops. Okay, I actually shifted it to my iPad by mistake, and I didn't mean to do that. I'm going to have to send it there. Oh, there it is. Now I can do the stop share. Okay, I meant to share my screen with you, and I hit iPad by mistake. Okay, right now you should be looking at Newton's first law of motion from our textbook and notice it says dynamics, Newton's laws of motion. What I'm actually wanting to turn to is this video from YouTube. It says Young Sheldon, first law of physics train experiment. Now it's about 1 minute and 21 seconds long, but I cut out the first 30 seconds so you could just see the part about the experiment. But basically Sheldon's telling about how he loves trains. And this is him as a young boy. And he actually does an excellent demonstration that I often do in my own class, only without a train. I have a little card that has a string on it, and the string's connected to a paper clip. And the paper clip sort of, you stick it in this hole, and that holds down a spring-loaded, basically foot that kicks a ball out of a vertical cannon. So whenever you pull that paper clip out, this vertical cannon, which is just spring-loaded plate, will push up on the ball and cause the ball to shoot up in the air. But if you actually take and roll the little cart first, then it's actually moving at some fixed speed. And then as soon as the string gets taut, the paper clip gets pulled. And because the paper clip's pulled, the ball shoots out. And then because Newton's first law of motion applies, the fact that it's moving forward in space and time as a result of the rolling cart says that the ball that comes out of the can is going to move forward in space and time. So let me show you this video real quick. Again, it's only about, well, I cut out the first 30 seconds of 1 minute 21. I figured out that trains allow you to prove Newton's first law. And object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. I felt like Neil Armstrong on the moon, alone and happy. I don't care how dim-witted you are. Scientific principles have to make you smile. Of course, nobody I knew in East Texas in 1989 cared about internal physics. The only things they cared about were women and cities. All right, so I think that's a pretty good intro type demonstration for the first law of motion, Newton's first law of motion. And in fact, it's one we normally do. Another one that we do is pulling out a tablecloth out from under a set table. So you can take a bunch of plates and set them out on the table, and then I whip it really quickly. And that's a little harder to understand why we're showing it's Newton's first law. But basically what you're doing in that case is you're realizing that the intention of the plates, the silverware, the cups, the glasses, all that good stuff is to stay right where they are. And if you actually apply a force, for instance, to the tablecloth and do so rapidly, then the tablecloth will actually try to apply a force to the items on the table, but the forces are so short-lived that they don't have much impact on the actual plates. So the plates and everything stay exactly where they are as you whip them out. So that's enough for that right now. Now I want to get into talking about Newton's second law. I've already stated what Newton's first law is, and in fact, I'm going to go ahead and share your screen with my iPad. So let me start sharing. And now you're going to see that I took the time to write out a version of Newton's first law of motion. Let me see here. And then we'll go into, of course, Newton's second law of motion and so on and so forth. So I have up here that Galileo's law of inertia and Newton's first law of motion are essentially equivalent. And what I stated really was closer to Newton's first law of motion. An object in motion will stay in that state of motion. That's a key point here. So what classifies motion? Well, what I'm saying that classifies motion is the concept of velocity, which we already learned about as a vector quantity. It has a magnitude and a direction. So you're not going to change the magnitude or the direction of an object unless you apply a net external force. Now, Sheldon said it a little shorter than that, and he said an unbalanced force. The reason why I included the word external and net is because net is really the equivalent of saying an unbalanced force. So the forces have to add up to give you something other than zero. If they come up to give you vectorially adding them, if they come up to give you zero, then the net force is zero. The other thing is the forces have to be applied to the object from another object. In other words, if you had a system, let's say a little boy in a shopping cart, the little boy and the shopping cart make up the system. So the little boy can't push the shopping cart while he's sitting in it to make the shopping cart go because that's an internal force. Now, the little boy could push off of a wall, and then by Newton's third law, that wall would be applying an equal but opposite force to him. And then he would be, of course, applying a force through that mechanism to the system, which is him plus the shopping cart. But in general, it's got to be an external force. That's the main thing. Okay. So an object in motion will stay in that state of motion, i.e. it'll maintain a constant velocity, i.e. its magnitude, its speed with which it's traveling will not change. It will not speed up or slow down. And its direction will not change. It will not turn left. It will not turn right. It will not turn up. It will not turn down. All of that stays the same unless a net external force is acting on it. So that's Newton's first law of motion. Newton's second law of motion is really what happens after Newton's first law of motion is found to be untrue. So, for instance, when you find Newton's first law of motion to be sort of untrue, meaning it's actually still true, but what we're saying is the conditions that allow it to not change that state of motion are now in place so that it can change that state of motion. So, what happens when a sufficient net external force acting on the system is able to actually cause the motion to change? How is that motion change? And that's what Newton's second law is. So let me write down Newton's second law. Newton's second law is the easiest to state as an equation. So I'm going to do so here, and then I'll explain it in words. So Newton's second law of motion says that the acceleration an object receives, A, is directly proportional to the net external force, okay? So you'll notice I have that sigma next to an F there. That sigma means summation. So add up all the external forces acting on it. And if I were to write this as a proportionality, which is what I just stated, an object's acceleration is directly proportional to the net external force, then what I would want to do is put a little, sort of looks like an alpha, a proportional symbol there. But we're not going to have to do that because we're actually going to add another factor, and then that's it. That's the whole thing. So I'm going to take that mark away, and I'm going to say the acceleration an object gets is directly proportional to the net external force, and it's inversely proportional. Oops. It's inversely proportional to the mass of the object. Thirdly, I will say that this equation is what we call a vector equation, which of course Newton didn't know anything about at the time. So what I'm going to do is go ahead and put the equals here because I don't need any other constants. The way we've got it in this system of units, the SI system, the acceleration is equal to the net external force divided by the mass. But the net external force and each individual force, of course, is a vector quantity, and the acceleration is a vector quantity. So you can also look at this as 1 over the mass times the summation of the forces. And the reason why I do it that way is just to show you that all we're really doing is taking the net external force, which is a vector quantity, and multiplying it by a scalar that is the reciprocal of the mass. So that actually gives you the net acceleration. Notice acceleration and net force, thumbs up, thumbs up. That means if the net force doubles, the net acceleration or the acceleration doubles. If the net force goes down by a factor of 10, the acceleration goes down by a factor of 10. Sorry, I can't lift my left arm so well, so I have to do it with with the same arm over and over. Plus, I've got something going on where Zoom knows to do thumbs up and do fireworks, evidently. So, yay! All right. So, acceleration and net force, thumbs up, thumbs up. And in this case, the exponent is exactly 1, like we talked about in lab this morning. The other part of it is the acceleration and the mass of the object are thumbs up, thumbs down. And in this case, the exponents are again 1, just like we talked about this morning in lab. But in this case, what we mean is if the mass of the object goes up by a factor of 2, then its acceleration is going to go down by a factor of 2. If the mass of the object goes up by a factor of 7.85, then the acceleration will go down by a factor of 7.85. So when the mass goes up by a factor, the acceleration goes down by the same factor, and vice versa. Any questions on that? Now notice it is a vector equation. So what that tells us is when you vectorially add all the external forces acting on the mass m, you get a single vector that has a magnitude and direction. Now you're going to take that magnitude and you're going to multiply it by the reciprocal of the mass. So it's going to change the magnitude completely, but mass can't be negative, so it can't change the direction at all. So we now see that the acceleration, not only will it have the magnitude of the net force divided by the mass, but it'll also have the direction of the net force. So that's why I write it as a vector equation. Anybody have any questions on that? So that's Newton's second law. And then Newton's third law is as follows. So we'll write Newton's third law. Of motion. So Newton's third law of motion says, well, probably there's 2 really major laws of physics that most people know, or a lot of people know, even people that aren't in physics. And one is Einstein's famous equation, which I bet you can guess, is E equals mc squared. The other one that is a lot less often known, but occasionally you'll even see it in tennis shoe commercials and stuff like that, and that's F equals ma, which is another way of writing Newton's second law of motion, which I can write like this. The summation of the forces is equal to mass times acceleration. That's another version. But there's in fact a third law of motion that a lot of people know. For every action, y'all could finish it right there in your head probably. For every action, there's an equal but opposite reaction. And that's sufficient. So I'll say for every action, let's say called a force, there is an equal but opposite reaction. the reason why I one put the parenthetical in there saying that it's a force is I wanted you to understand action actually it has a meaning in physics, and that's not what we're talking about here. I'm trying to use the terminology that you've used to being to hearing, and that's for every action there's equal but opposite reaction. Really what we're saying is this: if you apply force on object 1 as a result of object 2, then object 2 will receive a force from object 1, F21, such that F21 is the negative of F12 or vice versa. So what I'm saying is this part right here, the force on object 1 due to object 2 is equal in magnitude but opposite in direction of the force on 2 due to 1. So you can see the F12 means the force on 1 due to 2, and the F21 means the force on 2 due to 1. And you see that they are what we call an action-reaction pair. So for instance, one thing you got to know when you're trying to sort out what the action reaction pair is, you've got to know that the force that one of the objects is applying must be acting on the other object, period. So for instance, if I say I jump off the ground, then clearly, in order for me to jump off the ground, let's say I just do a standing jump straight up, then I have to apply a force to the ground in the downward direction. Okay. Now, when I do that, I'm actually applying a force to the ground. And according to Newton's third law, the ground's going to apply the exact same force that I apply to the ground. It's going to apply that magnitude to me. But in the case of me, the force is applied upward, whereas I applied the force downward. But notice I am acting on the ground and the ground is acting on me. That makes them an action-reaction pair. If, for instance, you fall out of an airplane or a helicopter or something, then gravity is pulling you down. Can you imagine or think of exactly what the other part of the action-reaction pair is? So something's pulling you down, and you have to find the other part of that. Can you think of it, Mr. Schlacky?
So, so you're saying what's the opposite force of when you're falling?
Yes.
It would be air resistance, or you're not falling in a vacuum.
That's normally what people say. It's not correct. Just because notice in that case you're saying I'm being pulled down, right. And yeah, there is a force up that's air resistance, like you're saying, and that is impeding my motion. So it meets the criteria of being opposite in direction, but only in the terminal velocity case does it meet the criteria of being equal in magnitude. But it also misses the criteria of I'm acting on it and it has to act on me.
So does it have to act on you equally as to the force that you're applying it, so that essentially they're equal, or they're equal in value?
Yeah, they have to be equal. Now, there can be a time delay. For instance, we know, for instance, that if this particular force is acting, it takes a few instances, basically nothing travels faster than speed of light. It takes a little bit of time when the force changes before the force changes that's acting on you. But in general, yes, the force that you apply to it must be applied to you, but in the opposite direction. So yeah, if it changes, it's got to change. But what is actually causing me to fall? Like if I was in outer space, really infinitely far away from anything, and I jumped out of a helicopter, which obviously couldn't fly in a vacuum, but just imagine I jumped out of a spacecraft, there wouldn't be anything to pull me. So what's
Right.
actually pulling me from when I jump out of the helicopter?
You have gravity,
The force of gravity. And what supplies that?
the mass of the Earth.
Exactly. So the earth is acting on me. And now that you have that, you just reverse the order. What is acting on the earth?
You.
Yep. So oddly enough, yeah, the action reaction pair, and this is perfectly normal, by the way. I just happened to know who you were because someone else was using a different name on their iPad. So I had to pick the person whose last name is their first name Josh or Josh?
Yeah.
Okay, Josh. Okay. So the action reaction pair both have to be acting on each other. So yeah, in this case, the earth is pulling down on me by the force of gravity, and I am pulling up on the earth by a force of gravity as well. It's actually equal in magnitude, but luckily the earth is kind of heavy, so it doesn't just readily move very much. In principle, it is moving. It has to move, but it's moving, in the 84th decimal place or some god awfully small amount like that. Weird, huh?
Okay. Yeah. So, but that only happens at the instance when you hit the ground.
No, it actually
Or
happens the whole time.
so
So
even when you're free falling and it's just you're in the air, gravity's on you, there still is a force that's being acted upon the Earth.
yes, yes, and in fact, you can see that at least by realizing that there's a force on me. Because if I'm falling towards the Earth, I'm accelerating, and if there was no air resistance, I'd be accelerating at 9.8 meters per second every second downward. And according to Newton's second law, you can't get an acceleration unless there's a net force. So clearly, the net force acting on me is important. That force we happen to call, it's a W word. Do you know what that is? Starts with a W. It's often considered one of our characteristics, like my particular characteristic.
Work.
Close. Something that I might be battling with because I got man boobs.
Oh, would be.
Weight.
Wait,
Oh,
there you go.
Yeah.
Thank you for picking that up, Carter. So yeah, because I have a weight, yeah, it turns out weight is due to gravity. We'll later show specifically what the formula for weight is, and that'll
Right.
come into play. So yeah, the fact that gravity is producing a weight on me or a weight of me, that is the force that keeps me accelerating, and therefore I'm also putting a force on the earth, and I am also trying to keep the earth accelerating towards me. And it's just, like I said, in the billionth decimal place or something. Okay. Now, there's another aspect of this which a lot of people don't get. So I want to give it to you. One of the things that we say, for instance, is have you ever tried to punch a square of toilet paper? Like you just take a single square of toilet paper and you let it fall and then you punch it and try to punch it as hard as you can. Probably no on that.
Maybe as a child, but not in my adult years. Maybe not.
Yeah, it's one of those weird things you might have done with just a sheet of notebook paper before in the past or something, but
Right.
that's basically the premise. But what you'll notice is you can swing with all your might, and you can't put much of a force on a piece of toilet paper or a piece of notebook paper. Or, like I like to argue, you can't put much of a force on a fly. So, for instance, you see a fly flying by, and if you have a fly swatter, that's nice because you can then swing with all the velocity that your hand would get in a regular overhand baseball pitch. But if you have an extension on the end of that arm, then you get even more velocity because you're
Yeah.
using fly swatter. In doing so, you get more velocity, and then when you actually hit the fly, your job is to hit it and then accelerate it until it reaches the same speed as the swatter or your hand. So the reason why it's so hard to kill a fly in the air by swatting it is because you can't apply any force any larger to the fly than it can apply to you. So that's another interpretation of the third law is you can't apply a force to an object any larger than the force it can apply to you. So just thinking about how small the fly is, it can't put much of a force on you, therefore you can't put much of a force on it.
Okay.
It looks like that internalized with you a little bit there, Josh.
Yeah. That makes much more sense, I guess, because I guess it doesn't matter the velocity. So I mean, you could have, yeah. So it's more or less it's the force that the fly can apply to you is the force that would be acted upon it.
Yeah, and that's that's a highbrow way of looking at it. I'm more of a details guy, so I like to do the nuts and bolts. So let me explain the nuts and bolts of it. Uh, if I'm, let's say, like a professional baseball pitcher, like this guy from University of Tennessee a couple of years ago was pitching like 112 miles per hour. That was pretty impressive. So let's assume that I can get my arm moving such that the tips of my fingers are moving at 112 miles per hour, and that I'm a really good aim. So I'm really going to hit that fly pretty darn hard. So what I'm going to do is I'm going to swing with all my might, and I'm going to hit that fly. And when I hit the fly, all I can really do to hit the fly is I can make it speed up until it reaches the same speed as my hand, and then it's just going to be sort of stuck against it and going like that. Sort of like if you got caught in a strong wind with a piece of plywood between you and the wind.
Yeah.
You're not much in control of the scenario there. So that's what's going on with the fly. But if you look at Newton's second law, you see, the acceleration I get is directly proportional to the force, but it's inversely proportional to the mass. And if I want to accelerate it, I'm going to have to change the velocity from, let's say, 0. That's a normal scenario. The fly is not moving appreciably with respect to your hand, so their initial velocity is 0. And you have to bring it all the way up to 112 miles per hour. That's a big change in velocity. So if you look at Newton's second law in terms of the F equals ma version that I have written in red there, you see that acceleration, which is v final minus v initial divided by the time taken, that acceleration could be quite large. But when you use F equals ma, the m has to be in kilograms, and the F is in newtons, and the a is in meters per second per second. So you can already see a typical fly is going to weigh on the order of grams, not kilograms.
Tiny.
So you're going to take that acceleration and divide it by essentially 1,000. And that large acceleration multiplied by that minuscule mass means the force is going to be very, very small. And that force is all the force that the fly can put on us as well. Does that make sense?
Yeah. Because they're proportional to
So if the
force and the acceleration are proportional to each other.
Exactly.
Mass is more or less the
reluctance to move or the inertia or something. Yeah. So if you hit a June bug, you have a better chance because a June bug is a fat little piggy, right?
Yeah.
Or if you hit, a really big I heard Richard Feynman called them needle bugs or something like that. We call them what are these horse flies? The things, not horse flies, but I'm thinking of the dragonflies. That's it. He called them nettles and needle bugs, stuff like that. But yeah, a dragonfly can get kind of heavy. You hit one of them suckers, they do a little bit more, and you can actually feel it on your hand because they weigh so much more than a fly does. So
and in that case, the mass is going up, and therefore the force would also be higher or greater than if under the same acceleration, then force would be greater if you were to hit a bug with greater mass.
Exactly. So so if you ramp that up and keep going till you hit a child, then you're talking about some real weight. Kids got whole kilograms of weight. An infant or a toddler or something like that.
So that would require So as the mass increases, essentially, the force would be having to go up exponentially almost, yeah, or not exponentially in literal sense, but
Yes, yeah, but that's exactly right. Like if the mass goes up by a factor of 10, guess what? The force is going to go up by a factor of 10. If the mass goes up by a factor of 10,000, then the force is going to go up by a factor of 10,000. So yeah, that's exactly it. So those are Newton's three laws of motion, and most people sort of think that Newton's third law is sort of the useless one that you never really use. But I can tell you an instance right now that is really important, and this is a typical question we'd ask. Uh, Pay close attention to my wording, both you and Carter. Uh, I can taking off of, let's say, the blocks like you'd use in a actual relay race or something like that for competitive running. I could take off and apply a force of, let's say, the unit of force, by the way, that we're using in the SI system is called the Newton, and 1 Newton is 1 kilogram meter per second squared. We're going to get on that, but essentially, a Newton is about a fourth of a pound. It's about as
Okay.
much as a uncooked quarter-pound hamburger. Okay, so that's a Newton, but I could probably put out 400 Newtons of force when I take off from starting blocks. So let me ask you this question. Mr. Younger can apply a force of 400 Newtons to the starting blocks to take off in a race. However, Newton's third law says the starting blocks are going to put a force of 400 Newtons back in the opposite direction. How is it possible that Mr. Younger can accelerate at all?
Well, the blocks aren't moving; they're stationary.
That's true. Yes.
I mean, I guess it wouldn't be proportional to each other if the blocks would move or slip or whatever. So essentially, it would be stationary if both of those forces were equal.
That works as well. Yeah, I mean those are important points, and that's really part of the trick here. But what you're missing is, remember the action reaction pairs. When I was falling from the helicopter, what was applying a force to me?
Gravity.
Gravity
Due to the
from
mass of
the
the
Earth,
Earth.
right? And what was I applying a force to?
The Earth.
Right. So you see that these two forces, action reaction pairs, are acting on two different bodies.
Oh yeah.
So when I apply a force of 400 Newtons to the blocks in the backwards direction, that's a force that I'm applying to them and should play no role in the Newton's second law for me. So for instance, in that F equals ma, where I put in m as my mass, the force that I'm applying to the blocks is completely irrelevant because that's not a force acting on me. But what is important is the Newton's third law says, hey, that force you just applied to the blocks are going to apply it back to you, and that's what makes you accelerate.
Yeah, I can kind of visualize that. I think because as I alluded earlier, because since it's stationary, it would be in theory applying force back to you.
Right.
And
If
that's
it
the
moved,
same
you wouldn't be able to take off at all, right?
Right, yeah, because it's similar to like, okay, I mean, I'm a runner, so if let's just say conditions are slippery,
Right.
the force you're applying to the ground for traction, essentially the slicker it is, the harder it is to gain traction and move forward.
Exactly.
So
in that case, it's the friction force that's limiting the amount of force you can that can be applied to you. You're trying to put out as much force as possible, but the friction force can't meet that demand. So you can only put out as much force as the friction force can apply to you.
Right, but if I were on a dry track that had a very rough coefficient, and I had full grip, then essentially the forces that acted upon me would be equal to the force that I applied to it.
Exactly. And in fact, they're always going to be equal to the force you apply to it. It's just a matter of, in the case of a low coefficient of friction, like you said, or like on an ice skating ring, the friction force is so small that you can't apply very much force to the ground horizontally or to the ice rink horizontally. Therefore, it can't apply very much force to you horizontally in the opposite direction. So yeah,
Well,
I think
because that work essentially, or that force or work is going to be dispersed somewhere, right?
yeah, you're trying, like your muscles are going to burn as much calories as you probably normally would when you tried to pull a full 400 Newton force. But in that case, it just accelerated your leg backwards instead of getting as much acceleration forward because the ground could stop it.
Right. Okay.
Does that make sense? All
Yeah.
right, so those are the three laws of Newton's motion, three laws of motion according to Newton. And like I said, he did say, if I have seen further than others, only because I stood on the shoulders of giants. I pointed out to you how Newton's first law of motion is essentially the same thing as Galileo's law of inertia. And I also pointed out that the law of inertia, the word inertia specifically, is just like a placeholder. It doesn't actually answer any questions. But in some sense, it gives you a feeling that, oh, well, maybe I'm not being so mean to Aristotle by just completely ignoring what he said, which, was entirely different physics than Newtonian and Galilean physics. So that's another way of thinking about it. Newton's second law was more or less him in its entirety. Newton's third law, as I told you, Leonardo da Vinci notebook said, it is obvious to anyone that if a eagle pushes down on the wind with a force of 50 pounds, then the wind's going to push forward or upward on the eagle with a force of 50 pounds. So we know that the third law was also already more or less reached by several people in the past, not necessarily Leonardo da Vinci, but in that sense, he's right. But also in the other sense, he is saying, if I have seen further than others, it's because I stood on the shoulders of giants, not hobbits like you, Mr. Hook. So, all right. Well, I think
Real quick.
Go ahead.
So let's just say, is it still, I guess, does this still apply to Newton's third law? Let's just say, I'm falling and I have a parachute and the parachute opens, but I'm still falling, but the air resistance that I'm acting against, or that is acting on me, or I guess just say, is slightly less than gravity because I'm falling.
Slightly less than your weight, as long as you're accelerating. Really, what the goal of the parachute is to bring you to a rather low terminal velocity. So what that means is the net force acting on you, which includes you and the parachute, is zero. So once you get to that point, then the net force is actually zero, and you are moving at whatever velocity you had when you reach.
But acceleration is zero.
Yeah, acceleration is zero there. But in the initial parts, when you first open it up, the air resistance is applying a force up, gravity is applying a force down, and gravity wins for a little while because you're going to accelerate for a little bit more until finally the parachute completely opens, and because of its large cross-sectional area, the air resistance is big enough to counteract your weight. That makes sense?
Okay. Yeah.
All right. So we have a nice conceptual example from your book. It says, Newton's first law: a school bus comes to a sudden stop and all the backpacks on the floor start to slide forward. What force causes them to do that? Anybody have any idea, Carter or Josh?
It's the fact that the bus was moving, right? So the force that actually stops them from moving would be the ground of the bus. Otherwise, they would just keep moving with whatever, speed they had reached with the bus.
Yeah, I think you're saying what's right. Not necessarily using the words that a quote unquote experienced physics teacher would use. And if I meet that guy, I'm going to bring him in and let him teach y'all. But there's not actually a force that causes the backpacks to accelerate. There's actually a lack of a force to keep it from going the same velocity the bus was going before. That's really what's going on. So if the bus was going 35 miles per hour and all of a sudden hit the brakes, the backpacks and all the kids' little heads and bodies are all going to try to continue going 35 miles per hour forward. But luckily, the kids are sentient and probably paying attention. So maybe they grab stuff. Most of them don't wear seatbelts, that kind of thing. But still, the main point is they would fly forward as well if it wasn't for other forces. Now, luck would have it that the friction force is not zero. It's not an ice skating rink as the floor
Right.
plus. So there is some friction force. So maybe the things slow down from 35 miles per hour, but it takes a little bit of time to do that. But that's really what it is. It's really inertia in some sense. The mass, which is a reluctance to slow down or speed up, is causing it to continue to go 35 miles per hour as close to it as it can anyways. Does that make sense?
Yeah.
So yeah, that's what causes that. It's the same thing that causes, like, if I stick my push mower in the back of my truck and I leave the tailgate down,
Yeah.
if I take off forward, the friggin' lawnmower is just gonna roll out the back. That's because the lawnmower
Yeah.
is perfectly fine sitting perfectly still, but when I hit my accelerator, between the wheels rolling and the minimal amount of friction between the bottom of the wheels and the truck bed, there's not enough force to keep it to go with it. So it just rolls instead of sitting still. Now, if I did that with a backpack, the backpack would probably almost stay still, but it would move forward a little bit slower than the truck does. Does that help?
Yeah.
All right.
Yes.
So that's a good first example of Newton's first law. I will tell you, your book talks in section 4-2-1 about inertial reference frames. And basically, when we study relativity, I've already mentioned to you what the two fundamental concepts of relativity is. The first is that the laws of physics are the same, specifically in special relativity, for all inertial reference frames. So special relativity says the laws of physics are the same for all inertial reference frames. The laws of physics are the same in all inertial reference frames. That's one rule. The second rule is the speed of light is a constant independent of the motion of the source or the motion of the observer. That's another one. But that first one is the one that is kind of interesting. But what Newton's doing there, or excuse me, what Einstein was doing there was saying, hey, as far as I can tell, I don't think gravity is necessarily a force. So if you're in a reference frame where gravity is causing something to accelerate, I'm going to say that's a non-inertial reference frame because obviously something's accelerating with no force acting on it. And that's really what he was trying to do, is cut out gravity. So that's why he said the laws of physics are the same for all inertial reference frames. When he goes to general relativity, he just takes out the word inertial, and that's the fundamental concept of general relativity. So what that tells you is we can do physics in non-inertial reference frames. For instance, when you take your statics and dynamic series, when you get to the dynamic series, you'll learn about these A dots and V dots and omega dots and R omega dot and all that sort of stuff. That's basically what comes from a rotating non-inertial reference frame. When a reference frame is rotating, i.e. connected to the Earth, for instance, that's technically not an inertial reference frame because we're actually accelerating in going from, let's say we're on the equator over here, and then a split second later, we're on the equator over here. We've obviously accelerated to some extent. So that's a non-inertial reference frame. So just be advised, if you're trying to make a coordinate system that you're going to solve problems in, you want to work really hard to make it an inertial reference frame. And that's one in which Galileo's law of inertia or Newton's first law of motion applies in. That's how you test it. Okay. I will say also that the Earth is almost always fair game as an inertial reference frame, even though strictly speaking, it's not an inertial reference frame, but it's really hard to detect the motion of the Earth for most experiments. So you can usually, a lot of times, use it as an inertial frame. Okay. All right, so now that we know, it's probably best that we not use non-inertial reference frames, and we certainly haven't been given the tools to use non-inertial reference frames yet. I will talk to you a little bit about mass. So mass, Newton called basically a quantity of matter. I hate that definition. It's not even a very clear definition, as your book says. I like to think of it as a measure of the inertia of an object. So an object's reluctance to change speed, its reluctance to speed up, its reluctance to slow down, its reluctance to change direction. That is a measure of the inertia and therefore the mass. And we use the unit of kilograms for that. So now that we have these three laws, I'm going to say, for instance, Newton's second law the summation of the forces is equal to mass times acceleration. And I'll tell you that mass, remember when I put square brackets around it, that's supposed to mean, hey, I'm just talking about the dimensions or the units. So I'm going to say the dimension of the meter is the unit of mass, which we call capital M, or the units of the mass is the kilogram. Okay. Yes, it has a prefix on it, but and we don't put kilograms. We call it a megagram. The main thing is because we very rarely interact with things that are on the order of grams, so we just use the kilogram as the fundamental unit. So that's what has to go in here. In Newton's second law, this has to be measured in kilograms. Now we've already learned that acceleration has a unit and a dimension, of course. So if I put brackets around the acceleration, I'm going to say the dimension is length per time squared. And I'll say that the unit for acceleration is meters per second, which is also meters per second squared. Okay. So from that alone, you can tell that the units of the force, which in this case is the summation of the forces, but of course you can't add two numbers or two objects unless they have the same units. So you know their units and dimensions have to be the same. So the units are the dimensions of F equals ma. The units of the summation of force has to be the units of the mass times the units of the acceleration. Or you can say the dimension would be the same as the dimension. So in this case, we'd say m times L over t squared. Or in the unit world, we would say the summation of the forces has units of the unit for mass times the unit for acceleration, which would be kilograms, meters per second squared. And what we say is 1 Newton is defined to be 1 kilogram meter per second squared. So that'll come in handy over and over and over again, because you'll find the Newton in a lot of stuff. And if you don't recognize it as a kilogram meter per second squared, you might not be able to get units that make sense. So anybody have any questions on that?
No, it's pretty straightforward.
Yeah, it should be pretty easy, right? Now, I will tell you the mass as a measure of inertia is a good thing. And it also happens to be a property of the object. So mass is a property of the object that doesn't change from one place to the other. Just like, you know, if I take aluminum, an aluminum block in the lab, it's going to have a very specific density. And if I take that to the moon, it's still going to have the same density. If I take that in outer space, it's still going to have the same density. And in fact, if I measure its inertia in kilograms, that's not going to change in taking it from the lab to the moon to free space where I'm infinitely far away from any planets. That's always going to be the same. But the other quantity that we sort of use interchangeably or synonymously is the weight, and that's very different. So I'm going to tell you that weight is the force of attraction between two objects that have mass. And I'll say it is measured in newtons. Okay. Now I'm going to apply Newton's first law in sort of the simplest scenario we can. Applying, actually Newton's second law, excuse me. I think I said first law. So if we apply Newton's second law in free fall, remember free fall is what we studied in chapter 2 and then more so in chapter 3. So what we know is that this object, let's call it object of mass M, we know it's going to be pulled downward by the force of gravity, which I just told you, weight is the force of attraction. And I could put due to gravity.
Yeah, I guess in our sense, in our universe, that's what, because the two forces are
Exactly.
the Earth and us.
Exactly. And if we were, for instance, on the moon, the Earth's still pulling on us, but the moon is closer and therefore has a bigger effect. Or if we're on an asteroid, nowhere near the Earth and moon, then the asteroid's going to be applying it. And that might not be very much at all. But yeah, that's the main thing. So we know that this force acting down is the force of gravity. And since I told you the force of gravity acting between two objects is called the weight, we can call that just plain W, right? And free fall means there's no air resistance or anything like that. So that's supposed to mean that the net force acting on it is just W. Would y'all agree with that?
Yes.
So Newton's second law tells us that the summation of the forces is therefore just equal to W. And if I wanted to make a coordinate system out of it and use vectors and all that neat stuff, then I might call this the y-axis, in which case I would say that this is negative W j hat or negative W y hat. That's the actual force. Okay. Now,
we're combining. So W essentially in this case equals mass and accelerations because it's mass and mass and the acceleration of gravity that are tied in together.
Right now we're just calling it W to find out what it's going to be equal to. But yeah, you know where it's going. That's exactly what we're doing. Okay. Does that make sense? All right.
Yeah, continue.
So you guys know what acceleration of object in free fall has? What acceleration is that?
Negative 9.8 meters per second.
Exactly. A is equal to negative, and let's just call it G, just because we want it to apply to all planets, and we can just call it G, and then on Earth it'd be 9.8, but somewhere else it'll be different, like Jupiter is essentially 3 times 9.8. Okay? So we'll just call that negative G, and it is a vector quantity, so I'm again going to call it negative G j hat or negative G y hat. Those vectors are completely not needed, but since I did stress that it's a vector equation, I thought I'd show it to you. Now, from that alone, we can take Newton's second law and from that and these equations, we get negative W j hat is equal to negative mg j hat, which tells us that W is equal to m times g, and that's the result we're getting. We were working for. So that's how you actually calculate weight, is you multiply the object's mass in kilograms by gravitational acceleration of whatever planet or object it's on, and that's the magnitude of the weight.
Okay. And the units just support basically what you said, right? Because if weight's unit is a Newton, you basically just calculated the units to be kilograms per times meters per second squared, which is a Newton.
Exactly. Yep. So we now have a useful formula, and we understand how the units work and all that good stuff. I did say, by the way, 1 Newton is approximately 1/4 of a pound, just for everyday life, letting you know that. Your book actually has some very specific conversion factors, that sort of thing as well, so you can check that out. What we're going to do now is we've now covered the section on mass, the section on inertia, and now we can actually apply Newton's second law in a useful way if my dog does stop barking. Chase, no, buddy.
Come on, Chase.
Come on, man, you're messing up stuff here. All right, so in general, we can take Newton's second law and it actually becomes, as a vector equation, it can become three scalar equations like this. I can say the net force is equal to mass times acceleration. And this version only works, by the way, for constant acceleration. And I say specifically constant acceleration vector. In other words, if I didn't have the vector, then what I want to do is, or if I didn't have a constant acceleration, what I want to do is say the summation of the forces is equal to m times dv dt, or m times d2. Let's call it r because I used that the other day. R the position vector over dt, and that fraction bar, of course, doesn't have to go under the m. I just did it because I'm kind of a moron. So, oops. Yeah, I hate that it keeps erasing stuff like that. Okay, so that's really the equation, Newton's second law, when you're actually dealing with a non-constant acceleration or a more general case. And this is almost completely general. Once we cover momentum, I'll show you a more general version because it turns out that it's not exactly right this way, but it's pretty darn close. In this case, the only case where it's not exactly right is if the mass is a function of time. More general, but mass supposed to not be mass as a function of time. If we had that, we'd have to do some other stuff, but that's close enough for what we're doing right now. I will tell you that in other systems of units, for instance, in the British system, which by the way, only us and, like I said, I think
I looked it up the other day.
Is it Liberia?
Yeah, it is. It's us and Liberia, and then there's like one tiny country. Hold on.
Like Sumatra or something crazy?
It was ridiculous. I laughed when I saw it.
I'm curious to find out what you said, what you found.
Oh goodness, hold on. Just keep going. I'll blur
Well,
it out.
I'm writing down here. Y'all can see it right now. I'm writing the units for mass in the three systems. There's a British system. There's the MKS system, which is also the System International, but it was originally called the MKS system because it's made up of meters, kilograms, and seconds. And before we had the SI system, we had the centimeter gram second system, and that's what I'm doing with CGS. So in this case, the unit of mass is the kilogram, and then in the CGS, the unit of mass is the gram. Then the unit of force is, in the British system, it's actually the pound. In the MKS system, it's the Newton, and in the CGS system, it's the dyne. So you've probably
it's us and it's us, Liberia, and Myanmar.
Myanmar, that's it, yeah.
Or Myanmar or Burma.
Yeah, Burma, yeah. So Liberia was one of them.
Yes.
Liberia's neat. It's got a little history that's really tied in with America. Like a lot of their places are named after our presidents and stuff like that. And Myanmar. So yeah, those are the only ones using that. But I will tell you, it's gotten pretty bad. Like I said, engineers really did not want to switch to the MKS system. So for instance, they have in the British system, they have something called the KIP. Have you seen that in your engineering work?
No. No.
That's the kilopound. They also have the MIP, which is the megapound.
Oh,
So yeah,
megaton.
it's gotten that bad. But anyways, I would say it's much better to just use the SI system. I will say, by the way,
wasn't
your
it
book,
because it would just be so costly to change over? Because like I thought in my last class, weren't they saying like in the wasn't like they made like a big push in the 70s to try and make the shift over to
yeah, late
the SI.
70s, early 80s, Carter tried to do it.
Yeah, but then they're like, it's just gonna be too chaotic as far as like cost goes because of just having to change everything. And like they would have to all the road signs would have to be changed, like even for speed
Yep,
limits.
it's not a cheap thing to do, but one thing that happened when the EU came along, the EU basically enforced a rule that said you're no longer allowed to sell products in EU countries that are doubly marked. They have to be marked in the SI system and only the SI system. So
Hmm.
they forced us to start printing things separately if we're shipping them overseas. So we're getting to the point where it might be more cost effective now to switch, but who knows?
Right.
Anyways, I will tell you, your book does a nice little footnote here. I will say that one dyne. And by the way, are you familiar with the dynamometer? You ever heard of that?
No.
Okay, a dynamometer is what you use to figure out the horsepower of a car engine or a boat engine or something like that.
Oh, Dino. Okay.
Yeah.
All right.
That's where
Because
that
people
came from.
say, oh, yeah, because I mean, I watch videos of, yeah, people putting their car on like quote unquote dyno.
Yeah, that's where it came from. The unit of force being the dyne. So 1 pound is 4.45 newtons, and one slug, which you can see for obvious reasons why here in America we do not announce to our wife that she weighs 9 slugs, as she would be quite unappreciative of the comment.
Yes.
So yeah, one slug's about 14.6 kilograms. And I hope this is a more enticing and inviting environment for females. That's what we're shooting
Well,
for in science.
do
Is
they
to attract more
don't they
females.
use like slugs with like metalwork and like, or like stuff with larger masses?
I think some industries might. I haven't done much with that, but I have heard the term bandied about a little bit when they're talking about slugs of raw metal, like they pull up as ores or something like that. But I'm not sure. I would say that would probably be the place where you'd find it. But in fact, we don't even use it here in engineers. If we want to find our mass, we'll divide that by 32 feet per second, and that'll give us
Yeah.
the number of slugs, and we'll call that pounds of mass instead of pounds of force. So we'll just completely skip the slug. Uh, so let's look at another example. Let's say estimate the net force needed to accelerate 1,000 kilogram car at 1/2 G, and then a 200-gram apple at the same rate. So here's an example for us. How much force is required to accelerate at 1/2 G a car of mass 1,000 kilograms, and B, a apple of mass 200 grams. So there's something we're going to compute here. And Newton's second law is pretty straightforward. The summation of forces is equal to mass times acceleration. In this case, we're just talking about one-dimensional motion, so we can just eliminate the idea of the vectors completely. And for part A, what we're going to do is we're assuming this is the only force required. So we're ignoring air resistance, friction, all that sort of stuff. We're just trying to say, what's the force that I have to do over and beyond those forces that we'd have to overcome? So in that case, I'd say the force, the total force, has to be equal to 1,000 kilograms, which I'm going to treat as if it's 4 sig figs, times 1/2 times 9.80 meters per second every second. And when I do that, 1/2 of 9.8 is 4.9. So I get 4,900
900
newtons.
Yeah.
Does that make
So
sense?
you would, yeah, you do the same thing for the apple, but convert to kilograms, right?
Right.
So you get
Yeah, that's the
0.9.
key point is you got to convert to kilograms.
Yeah.
So
Well, for the apple, is it half G or is it 1 full G?
1/2 G in both cases. They're both looking for the same rate.
Okay.
So this one be 0.200 kilograms times 1/2 times 9.80 meters per second per second. I don't know why I switched to red, but anyways, we can now see 4.9 times 0.2. That's 0.49 times 2. That's 0.98.
Yeah.
And that would be our answer for part B. Make sense? So
Yeah.
that's really that example from your book and authors is really just to show you, hey, yeah, you got to use kilograms. You can't use other things. Okay. There's another example. It says, what average net force is required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? So that's another example.
Distance 55.
You're helping me a lot there, Cosmo. I appreciate it. Or Chase, sorry. What average net force is required to bring a 1,500 kilogram? Notice you have to put a dash in it when you're calling it like a name, a 1,500 kilogram mass, a 1,500 kilogram car to rest from 110 kilometers per hour. No, 100 kilometers per hour. Sorry about that. I'm going to treat that as if it's 3 sig figs. And I'm going to treat 1,500 as if it's 4. From 100 kilograms per hour. To 0 within 55 meters. Okay. So this one's going to require us to do a little bit of kinematics as well. So here's our solution. I'm going to treat this again as one-dimensional motion. So I have the summation forces in, say, the x direction is equal to mass times acceleration in the x direction. Basically, that's what you do. If you have F equals ma as a vector equation, you can then write F equals ma with subscripts x, and then another one with subscripts y, and then another one with subscripts z. But the other equation we're going to use is Vf squared is equal to V0 squared plus 2a x minus x0. We're going to use that specifically because we're only given the distance over which it traveled, and we're supposed to find out, basically what its acceleration is. So I'm going to first off, I'm going to take the 100 kilometers per hour and I'm going to convert that to meters per second because I can't use it unless it's in meters per second. Now, what I know is there's 1,000, or excuse me, there's one, darn it. Sorry, I can't get it to disappear. Okay. There's 1 kilometer in every 1,000 meters. So that'll convert the kilometers to meters. And then I can also say that there's 3,600 seconds.
Seconds.
Yep. And what I'm going to do is say 1 hour is equal to 3,600 seconds. And then we can see in this case that the hour cancels out with the hour like that. So basically, to convert from kilometers per hour to meters per second, I just divide by 3.6. So when I do that, I get 27.8. And actually, I like to carry one extra sig fig. So yeah, it's 7.8, I guess. Yeah. So we'll do 27.78. I was stealing the book's version, but I'll put it like that. And I'll say this is meters per second. Now I can say that A, according to the kinematic equation, A is going to be VF squared minus V0 squared over 2 times X minus X0. But I'm going to go on the assumption that X0 is 0. And I also know the final velocity is 0. So I'm going to get a negative value. That's okay. That's
That
going
makes
to
sense.
Yeah, exactly. We chose probably a direction in which the thing was moving in the positive direction. So this will be 27.78 meters per second squared with a negative in front of it, divided by 2 times 55 meters. So divide, or actually square that first. So I squared the 27.78 and got 771.6 negative. Now that's 4 or 5 sig figs, and we're only really allowed to have 2. So I'm going to put that here, and that's meters squared per second squared. And then I'm going to divide that by 110 meters. And that gives me negative 7.0146. And that acceleration is meters per second every second, which is the way I like to think of it, even though meters per second squared works. Now all I have to do is put that in F equals ma. So the summation of forces is what we're looking for. That's equal to 1,500 kilograms times 7.0146. This 4 and this 6 were not sig figs. And here's a good place for us to write it as meters per second squared. So we'll see that it comes out into Newton. And for this one, I get 1.05 or 1.05 times 10 to the 4th newtons. And that's to the proper number of sig figs. It was actually 1.0521 times 10 to the 4th newtons if you wanted extra digits. Does that make sense?
Is that negative? I'm sorry, I was probably writing some down and you mentioned it, but is that negative not applying?
You could have put negative or you could have put positive. Since I'm really just asking for what the net average force was, there was no value in me having the negative. But if you wanted to, you could just say in the opposite direction that it was going.
Okay, so if you clearly state that it's in the opposite direction, that would suffice.
Yeah.
But if not, like the short answer would just be negative 1.0 or 1.05 times 10 to the 4th.
Exactly. So that's just in the opposite direction of the velocity, initial velocity. Does that make sense? I think that's pretty straightforward, right?
Yeah.
Yep.
All right, so we don't have too terribly much more time. What I want to do now is do some very specific examples, just so you can get an idea about what kind of forces we're going to deal with. So for instance, your car does, or your book does this example, a conceptual example. It says, what exerts the force to move a car? Can you guys think granularly enough to figure out where is the actual force applied to a car that's, let's say, accelerating?
And it's the combustion of the engine.
That's normally what people say.
Well, it starts there, but then it goes through a series that applies, I mean, to the axle, which then turns the wheel.
Right. You're getting closer because right now everything you said is part of the car. That would normally be part of the system. So those are all internal forces.
Okay.
So then it's the road.
There you go. Yeah, that's it.
What?
Actually, yeah, isn't that weird? So what
The
happens?
road is.
Yeah, the road's pushing you forward. If you don't believe me, try parking on an ice skating rink and see how good the road
So
is.
okay, yeah. So it kind of goes back to the friction type deal, where essentially it's the force that's acted upon. Yeah. Okay. All right.
Exactly.
That's awesome.
When you hit the accelerator, you're telling the tire to basically spin out or just to rotate really rapidly.
Rotate.
And if there's insufficient friction, you're just going to spin out and not go anywhere. But if there is sufficient friction, then it's going to apply a force to the road due to that friction. And then Newton's third law says that the tire applies a force of 10,000 newtons to the road, means the road applies a force of 10,000 newtons to the tire. So yeah, it's actually the road. Crazy, huh? Yeah, that's a very easy question to miss. And like 99.9% of people taking their first physics course will get that wrong every darn time. And it seems perfectly reasonable to get it wrong, right? Yeah, it's clearly the engine that's doing it, or it's the torque, or it's the transmission, or the tires. But anyways, let's go on to they do a question. It's called Michelangelo's assistant. Basically, it's third law of clarification. So make sure y'all read over that one.
What section?
I'll say read conceptual example. And that's conceptual example 4-5. All right, darn it.
That's 5.
Darn it. So that's
the block on the sled.
That's sort of like the question I just posed to you about me and the starting blocks and me applying a force of 400 pounds and so on and so forth. So we've already worked out the gravitational force, but what I need to do is something along the lines of, let's say, accelerating a box. So what happens when a person pulls upward on a box with a force equal to or greater than the box's weight? For example, let the force be 100 newtons and rather than 40 newtons, which was in the previous example. So what I'm going to do here is I'm going to draw a box and imagine a force on it. So this is similar to a problem that we have in our book. So what we're going to do is have a box sitting on a surface like this, and the box has a mass, or a weight, excuse me, W equals 40.0 newtons, like that. That's its weight. And we're going to apply a force of, let's say, 100 newtons. And we're going to apply that at an upward angle. And in this case, we're going to apply it at an upward angle of, let's say, I'm going to use our famous 3-4-5 triangle. Oops, but I ended up pushing the wrong button like a crackhead. So,
isn't that like 56.13 degrees?
53.13 was the one I was thinking of, but I was going to do the smaller of the two, which is 38.16 or something like that. I never can remember. 36.87. There you go. So let's say this is 36.87 degrees. Okay. Now, the reason I use that is because the 3-4-5 triangle is really wonderful. And what we have is a 3 here and a 4 here and a 5 here and 36.87 there, which can also become 100.0 newtons. But clearly I had to multiply 5 by 20 to get that. That means I have to multiply 3 by 60 or 3 by 20 to get that, and 4 by 20 to get that.
20.
Yeah. So what this tells us is, okay, I can now draw what's called a free body diagram. And this is absolutely critical for you to do a Newton's second law problem. So what we're going to do is we're going to draw the mass, which, by the way, 40 divided by 9.8 gives me 4.082. Actually, I don't want to write it there. 4.082 kilograms is approximately the mass. And the forces we have acting on it are a force of gravity, which is in the downward direction, which I'm going to call a negative direction. And that force is the weight, which equals 40.0 newtons. And then this one's going to be kind of weird to you, possibly. There's actually a force that the ground is applying to it. Even though the ground's an inanimate object, the ground is applying a force that we call the normal force. And I normally write that as F sub n. Your book tends to call it just plain n. But you can realize that by, if you try to sit an elephant, for instance, on a table, you realize that the table is not up to holding up the elephant and it'll quickly collapse. But you can put an eraser on there. So clearly the table is able to apply a force, and that's what the normal force is. Now, the other force that we're applying is, in fact, I'm not going to draw it green or red because it's not along any axis that I plan to use. It's actually this force right here, which is 100.0 newtons at 36.87 degrees. And now I'm going to draw my coordinate system, and I'm going to draw it in black. So this is going to be my positive x-axis, and this is going to be my positive y-axis. And now I'm taking Newton's second law. The summation of the forces is equal to mass times acceleration. That's going to be the summation of the forces in the x direction is equal to mass times acceleration in the x direction, and the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Now, we're imagining this block or this box, whatever it is just sitting on the ground, and I'm going to start pulling it, and it's going to slide left and right. It's not going to move up and down, though. I mean, if it had a real bumpy ground, it would be, but I probably would have mentioned that. So, in fact, its velocity vertically is going to be 0, and it's going to remain 0. So because of that, we can say the acceleration in the y direction is equal to 0. The main thing I'm trying to say here is this equation right here, which is a vector equation, becomes these two because it's clearly a two-dimensional problem. So now I'm going to take the summation of forces in the y direction equals 0. That's going to give me F normal minus 40.0 newtons. Now notice the left-hand side says the summation of all the forces. I just wrote subtraction. I hope you understand that that really means this is plus, but it has a negative sign for the magnitude or for the direction. Yeah. So that's the key thing I wanted you to get out of there. And all of this is equal to 0. So that means you've got that the normal force in this particular case is 40.0 newtons. We didn't really need it, but we will later. And turns out that friction force is proportional to the normal force. So normal force is something you're going to have to calculate quite regularly. But we have that. So that's an answer. We just didn't need it. Now I can apply the summation of the forces in the x direction equals mass times acceleration in the x direction. In this case, what I'm going to get is really there's only, oops. I forgot something. Anybody realize what force I forgot? I never broke my 100 newtons down into components in the x and y, so I completely left them off. That was bad. So yeah, sorry, I screwed.
Because that's the vector. Yeah.
Yeah, that was all my screw up. I apologize for that. I was fixated on worrying about the signs without paying attention to the bigger picture. Go ahead.
Yeah, so we need to find essentially the scalars.
You're right.
The vector components.
Exactly, which I sort of already did by writing it in the red triangle over there. In other words, that component is green because it's pointing in the positive direction. And this component is green because it's pointing in the positive direction. And we know this one's going to have to be 60.0 newtons. Actually, we can call it 60.00 newtons. And this one's going to have to be 80.00 newtons. Okay. Now I can do the X component. I'm sorry about that. That was a real bad.
That makes sense. No, that actually helps.
All right. So the summation of forces in the Y direction is equal to mass times acceleration in the Y direction, which turned out to be 0. Now this gives us, this time we see that we have the normal force pointing upward. So we're going to call that positive. And then we're going to say plus, we have another force pointing upward. That's the 60 newtons. And then we have another force in the Y direction, but in this case, it's in the negative direction. So I'll say plus negative 40.00, or actually that should have been 10 because that's one they gave us. Newtons, and all that equals 0. So we can see that by pulling upward a little bit instead of just horizontally, we actually took away some of the normal force. And that would actually help you because the friction force turns out to be proportional to the normal force. So if you decrease the normal force, you decrease the friction. So there is some advantage to actually lifting up a little bit. You can actually.
That makes sense. Because an object's really hard. So say if you're pulling across carpet.
Exactly.
And there's that friction from carpet. If you pull up a little bit.
Yeah, you can. Yeah, there you go. So now we get that the normal force, instead of being the 60 newtons that I had said before, which oddly enough did actually help, the 40 is going to come to the other side and be a positive, and then the 60 is going to be a negative. So the normal force is like negative 20, which doesn't really make any sense, obviously. But the main thing is you're saying that the table does not have to supply any force whatsoever because I applied such a big force there. Okay. So I'll just say, okay. But the more important thing is we want to figure out the acceleration, and we probably wouldn't have calculated the normal force at all normally on this problem. I just wanted to show you how to do it because it's more complete. So let me go ahead and do this and say the summation of forces in the X direction equals mass times acceleration in the X direction. Again, the right is the positive direction, just like up was the positive direction. So in this case, I have 80 newtons. Actually 80.0 newtons, 0.00 newtons is equal to 4.082 kilograms. Notice I had to actually use weight equals mg, says m is equal to weight over g. That's how I got that mass. And then all of that times the acceleration in the y and the x direction. So the acceleration in the x direction is 80 divided by that 4.08, so I get 19.6. And that's meters per second every second. Now, here's where I usually tell you guys that the importance of keeping that in meters per second is strictly because just because we finished doing kinematics does not mean that we're done with kinematics. For instance, I can now say part B of this question, how fast will the object be going after 1 second? And of course, you'd say 19.6 meters per second. And then I could say, okay, well, what distance did it travel in that 1 second? And you'd say, of course, 1/2 times 19.6 times 1 times 1 being 1/2 AT squared, right? The initial velocity being 0. So all of that's fair game, but by recognizing that it's 19.6 meters per second, you realize after 1 second, it's going to be going 19.6. After 2, it's going to be going twice 19.6. After 3, it's going to be going 3 times 19.6, so on and so forth. Does that make sense?
Yep.
Yeah.
Okay. So this problem, like I said, did have a Y component that I should have probably not messed with because I just made it up. And in so doing, I made a situation where I'm actually going to be lifting it up off the ground to some extent, which is kind of a problem. So ideally, what you'd want to do is probably not pull it up at that steep of an angle, or use a smaller number of newtons. In other words, maybe do a 50 or 60 newtons instead of an actual 100 newtons. But either way, we did see how the mechanics of working out the components of the forces worked out and how you got an acceleration from that. Here's another neat problem. We're supposed to be over about 250, so I want to try to use that. But like I said, if you guys got to go, that's cool. I understand. Well, I don't know what happened to this. So maybe I've just used too many pages. Okay, so in this case, let's actually imagine an elevator, a little box that represents an elevator. And what I'm going to do is I'm going to put a little scale in that elevator. I'm going to put a person in there. And I'm going to say the person has a mass M. Okay. Now I'm going to draw my coordinate system arbitrarily. Remember, you can always draw a coordinate system any direction you want to, but there's some that are really a lot easier than others. So it's always nice to have at least one axis parallel to the motion. What I'm going to do is I'm going to say, if the elevator accelerates upward at A equals, let's just say at A, what will the scale read? B, what if it accelerated downward? And then C, give both answers. Or A equals 1/2 G and M equals 70.0 kilograms. Okay. So again, the free body diagram is the most important aspect of using Newton's second law. So in this case, I really want to think on the microscopic level, like, hey, what is the force that crazy scale is going to be applying to the bottom of the person's feet? And then the person's feet, of course, is applying a force to that scale as well. So that's the system I'm actually thinking of. So what I'm going to do is I'm going to say, here's a mass of 70.0 kilograms. And then acting up on it is a force, which is in the positive y direction, according to the axis that I've made up. And that's going to be the force due to the scale. And I'm going to have a force acting downward that is the person's weight. And I put that 70 kilograms for part C. Obviously, we're just using M for part A and B. Okay. But the other thing that's going on here is I want you to understand that for part A, the acceleration is up, and for part B, the acceleration is down. Okay. Now I'm going to go back and assess my coordinate systems. So this is the positive y-axis, and this down here is the negative y-axis. So for part A, what I'm going to get is the summation of the forces in the y direction is equal to mass times acceleration in the y direction. Oops. So that's going to give me Fs, which is what the scale will read, minus mg is equal to M times, in this case, A, because A is in the positive direction. So I'm just going to say MA. So we see that the FS is equal to M times A plus G. So that's the answer for part A. So you've probably felt this before when the elevator first takes off, especially if you're sort of light, like not holding your knees locked, you'll feel your knees sort of give in a little bit because the earth is, or the elevator's going up and the earth is pulling you down, and you actually have to apply a little bit more force than just your weight. So that's what's going on there. Now, when we try the other one, the same sort of thing happens, only now A is in the negative direction. So we're going to say Fs minus mg in this case is equal to negative m times a. Again, when we put it in scalar form, the plus or minus is basically giving us the direction. So I had to include that negative a there. When I solve this for Fs now, I get Fs is actually equal to m times, this time it'll be g minus a instead of g plus a. So that's the answer for part B. Now, 70 kilograms is about, well, it's times 2.2, so it's 140, maybe 156 pounds. So about 156-pound person is what we're talking about here. So now let's do part C. And for part C, we're going to do Fs sub A is equal to m times g plus a, just because I wrote it in that order. In part B, I decided to change the order here. So in this case, it's going to be 70.0 kilograms times 9.80 meters per second per second. In this case, it's plus. Notice it's 1/2 g, so I'm going to say 4.90 meters per second. So now I can do 9.8 plus 4.9. Oops. I did multiply. That's not good. 9.8. Oh, I did multiply again. Plus 4.9 gives me 14.7 meters per second times 70 gives me 1,029 newtons. And of course, that's supposed to be 3 sig figs. Actually, you get 4 sig figs out of this and then 3 sig figs there. So it should only be 3 sig figs. So it'd be 1,029 newtons is what you have to apply in going up. Well, and then for part D, or excuse me, still part C, my fault. Fs sub B is going to be m times g minus a. So in this case, it's 70.0 kilograms times 9.80 meters per second minus 4.90 meters per second. So we're obviously going to get a lighter mass this time. So 9.8 minus 4.9 is equal to 4.9. Multiply that by 70. That gives me 343. And W, by the way, is just 70 times 9.8, which equals 686. So you can see that considerably less force is required. In other words, you're going to read an apparent weight of 343 newtons when you're going down, and you're going to read an apparent weight of 1,030 newtons when you're accelerating upward. When it's actually moving upward without acceleration, it's going to read the regular 686 newtons, though. Does that make sense? All right, there's one more problem that I need to make sure you guys already know. So let me just get you started on that one real quickly. It's basically an inclined plane problem that we're going to study over and over and over again. So let's imagine an inclined plane. And let's say this angle is 30.0 degrees. Let's say we have a block right up here. The mass is 40.0 kilograms. And what we want to know is what is the acceleration downward if there's no friction. Or actually, let's assume the friction. Let's assume the friction force is 3.00 newtons. What we're trying to figure out is what is the acceleration down. Okay. This case, I don't really need the normal force, but I'll do it anyways. It turns out when you're working this kind of problem on an inclined plane, it's really good for you to use a tilted coordinate system. So I'm going to draw X pointing down the incline, parallel to the incline.
Are you going to make that X direction positive?
Yep. Just because that's the direction it's going, and I don't like having negative numbers unless I have to.
Yeah, that makes much more sense.
Yeah, and you can do it the other way. It's fine. It's just everything will come out a little bit more negative. Okay. When we do this, though, of course, you still have the same problems. And until we start studying torque and all that stuff, we have to pretend the object is a point object, like a little mass M here. So this is our little 40.0 kilogram mass there. And we have acting on it a force that is straight down and therefore not parallel to either axis. That force is the weight W, which equals M times G, which is 40 times 9.8. That's going to be 392 newtons. And this axis is tilted at an angle of 30.0 degrees, which you can realize if you look at, let's do some red lines here. Or actually, I'll do a little red line. So you can see right here, this is a right triangle. So this little angle right here would be 90 minus 30, which is 60, the little red one. But notice that from there to here, that's a full 90 degrees. So that means this one has to be 30.0 degrees. That's a key thing to understand about this diagram. Now what I can see is there's going to be a negative component of the weight in the negative y direction, points that way, and that one's going to be 392 newtons times the cosine of 30.0 degrees. That's its magnitude. Of course, it's going to be negative too, but that's the main thing. And now there's also going to be a positive component of the force in the x direction, and that one's going to be 300. Oops, let me make that a little clearer. That's going to be 392 newtons times the sine of 30.0 degrees.
All right.
Does that make sense?
So yeah.
Go ahead.
Why are we doing it that way rather than using the triangle to the left?
Because that one didn't have the force, the purple force mg on it. I needed to get a mg that can be interpreted as a x component and a y component. So I had to complete a right triangle going from the tail of the w vector to the head. So I went down that red one and then to the left down that green one, and that got me to the head of the mg. That makes sense?
Yeah, it's different now that everything's tilted, so
Exactly. That's
it's gonna take some getting used to.
Yep, that's all. And here's the friction force, which is going to be 3.00 newtons. And then also, here is the normal force, which we can solve for as well. Okay, doesn't necessarily help us because we've already got the friction force, but we can do it anyways. So I'm going to go ahead and say the summation of the forces is equal to mass times acceleration becomes the summation of the forces in the x direction equals mass times acceleration in the x direction, and the summation of the forces in the y direction equals mass times acceleration in the y direction. But again, I'm not picturing this block bouncing up and down on the or on the diagonal plane. It's actually going to stay at the same height above the diagonal plane. So that acceleration is going to be 0 there. But the main thing is we now have the two equations of motion. I'm going to start off with the force in the y direction just because it's the easy one. And I wanted to get it out of the way. So we've got the summation of forces in the y direction is equal to 0. I have converted all my vectors into components parallel, so I won't forget any of them. And I see that I got a positive normal force, Fn. And then I got a 392 times cosine 30. That gives me 339.5. That's one extra sig fig. So I'm going to say for this one, it's going to be plus negative 390 or 339.5 newtons that way. And that seems to be the only one in the y direction. So that's equal to 0. So I can now see that the normal force is equal to 339.5 newtons. Okay, so notice that is also equivalent to mg cosine 30. That's a very normal result if you're measuring the angle up from the horizontal. That's the normal result for the normal force, unless you had something weird like a rope pulling up on it relative to the hypotenuse of that triangle. Now I have the summation of forces in the x direction equals mass times acceleration in the x direction. That's the only acceleration. It's the acceleration we want. So I stop subscripting at x and just put a there. With this one, I get a force of 392 times the sine of 30. That gives me 196. And that's in the positive direction. So I'm going to say positive 196.0 newtons minus 3.00 newtons is equal to, now we know its mass is 40.0 kilograms. And the A is what we're wanting. So A is going to be 196 minus 3. That's 193.0 newtons divided by 40.0 kilograms. And that gives me 4.825 meters per second every second. So that's the actual acceleration that it has down the incline. And that's all I wanted to get through to you guys, is I wanted you to see how to draw a free body diagram, how to choose your positive, negative directions, how to break your vectors up into components parallel to the axes, and then, of course, how to solve them. We're going to do a lot more problems the next time as well, so this should get you started. If you have any questions, stick around and ask them. Right now, you're free to go, guys.
Thank you.
Thank you. Appreciate you coming. I'll post this. I might not be able to post it till tonight. No, I think I can post it now because I got 2 hours before my next class. So it'll probably be posted in about an hour or so.
Huh.
Any questions, Josh?
Thinking. How do we apply the friction?
In this case, I just drew it pointing parallel to the inclined plane, but pointing in the opposite direction of motion. That's normally how we do the friction, is it's going to be the opposite direction that the thing is moving. So
So
you don't
it's
know.
applied in, yeah, okay, so we subtract it.
Yeah, it's always in the opposite direction of the velocity. So if there's a question, like if you have a mass hanging over a pulley that's hanging off the end or something, you don't know if that mass hanging off the end is enough to pull it up the incline or too little so it slides down the incline, in which case you have to check both scenarios and see which one it is, because the friction is going to be the opposite direction. So that's something you got to keep in mind, because that doesn't mean that means the friction could sometimes act up the incline, or other times it's going to act down the incline.
Ugh, this is crazy, but it's fun.
Yeah.
So explain the two dots. real
Okay,
quick.
I'm just using the two dots as to break up the line. Normally I'd do an arrow, but I didn't have enough room, so I just put a colon to say,
Okay. All right. Okay, that makes sense.
gotcha.
All right.
I'm just putting it there to say, hey, this is what this equation begets,
Right.
because we just don't use the word.
Okay. And these are, yeah, we start doing these in chapter 4.
Yep. This is chapter 4.
Okay.
Next time I'm going to show you an Atwood machine. I'm going to show you like fuzzy dice hanging from a rearview mirror of a car, because both of those
Yeah.
give us these very specific techniques that are specific to physics, but you probably would have never learned in your actual math classes about how to solve systems of equations. And for good reason. There's good reasons that the mathematicians often don't tell you to do it. They'll do it themselves when they know it's okay, but they hardly ever teach it to you. So I've got to show you a couple techniques, and that's what we're going to cover.
Yeah. This is wild because, like, I mean, this is totally different than learning theory. Because, like, with theory, at least with, like, in my calculus book, there was like all of these, physics problems
Right.
that were like it worked into all the examples, but this is more opens up like everything that I've learned in math theory and brings it to a whole nother, applies it in a wonderful way that's much more applicable than just learning straight theory.
Yeah, you got to take forces, and you got to decompose them into vectors components, and then at the end you might even have to recompose it back into a vector depending on what they're asking for. Then you could also have be asked kinematica questions. You could be asked to compute a friction force. You have to figure out which direction the friction force is acting based on the information they gave you. All sorts of crazy stuff.
Yeah, it's awesome. Yeah,
All
physics is fun. It's really fun.
I'm glad you like it. It should be fun. Yeah, shame
All
you
right,
missed
well,
the Sheldon video at the beginning.
Oh yeah. Oh, did you show something?
Yeah, I showed this right here, which is just a young Sheldon.
Oh.
Actually, it's kind of cute. I'll do it. Hold on. You can hear it right now, but hold on.
In fact, if my career in theoretical physics hadn't worked out, my backup plan was to become a professional ticket taker or hobo.
He loves trains.
Brains allowed me to prove Newton's first law. An object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. I felt like Neil Armstrong on the moon, alone and happy.
That's cool.
Scientific principles. Of course, nobody I knew in Texas in 1989.
That's crazy.
She's done it.
That pretty good?
That's awesome. Yeah.
All right. So hopefully
well,
that
and then
the first law. Go ahead.
Yeah. On Thursday, well, for one instance, the lab that's all we could just use that using Excel.
Yeah, absolutely. There's one part where they ask you to hand draw one, and I ask my students to do the same thing. Just because you want to go through a little bit of that headache of trying to maximize the scale so that you can use up as much of the width of the paper and as much of the height of the paper to make the graph as big as possible. And then, of course, you're going to turn in a photograph of it. But the main thing is that one that should be linear. In other words, make sure you graph a linear one by hand using as big a scale as possible to use up, let's say, 80–90% of the paper. And then draw, using a clear ruler, draw a line of best fit, and then compute what y equals mx plus b is for that particular one so that you can compare it to what Excel gets. But other than that, it's the same thing. And I've got
Okay.
2 student groups that are going to send me data so you can actually do it to make up for the one you missed.
Okay, and then also one more thing. Thursday I have a work event that I have to attend. So I will be out for lecture and lab. I saw we're doing linear. We're essentially doing the same thing, but it's the second part for lab.
Yeah, that's what's next time is linear graphing 2. And I'll
Okay.
see if I can. If you have to miss, I'll see if I can get some extra data that will let you analyze for the lab portion. You'll still get points off for having to miss the class, but not much.
Okay. Yeah. Okay. All right. Sounds good. I'll email you if I have any questions.
All right, and remember, if you need these notes, they're on my Google Docs page that you have linked to up in the useful links and information.
Yeah, I've been there before.
Okay, that's
So,
cool.
All
Have a good
right.
one, Josh. Talk to you later.
Yep. Thank you.
You're welcome. Bye-bye.
All right. Bye.